Which one? This one, green. Okay. Okay. Good that I did this part. Now we are set on our color. Okay. So what we are going to do today is learn how to do the knapsack problem that you talked about in class. In class session or the session before, or in one of the previous sessions, really. So let's look at a generic. Well, I think we discussed it in class that the knapsack problem is not a easy problem to solve. Normally. Well, knapsack per se might not be that hard, but it's just that it falls into the category of the problems that might be hard if you make it integer or non-integer. You need to enumerate some cases to do things, and I think you talked also about this intelligent enumeration methods that you just don't go and count everything. You just count some of them and make sure that it works for everything. So we are going to do one of these methods. It's basically a very, very generic method to do a lot of problems, and a lot of problems fall into this category, and it's called dynamic programming. So we are not going to discuss it that much today. We're going to look at an example, see how it works, and then you're going to cover it in class in detail. But I think it's going to be a good start. And then after that, if I have time, which I think I should have because this shouldn't take a long time, we will talk about the active set methods a little, just to recap whatever we have learned in class. So if we look at a generic knapsack problem, it looks like this. Maximize sum over I from 1 to n. Okay, just to keep the same notation that I have here, j, cj, xj, while summation of all of them, aj, xj is less than or equal to b, and xj is either 0 or 1 for all j. Okay, so this is what we call the knapsack problem. Basically, we gave an interpretation to it that we have a knapsack, but my knapsack doesn't look nice. And obviously, it has a capacity, and then you have certain objects. Different shapes, okay? And each of these objects has a value. So each of them has a value, which we call it C1, C2, C3, C4, and C5. And each of them has a weight, volume, some kind of physical characteristic, okay? And then our knapsack is limited in that characteristic. Since my knapsack is nice, I don't want to deal with the problems of shape. Let's say that it's the weight that we are discussing, okay? So each of them has a weight in our case. You can put it anything, it's not really important. This is A1, A2, A3, A4, and A5. And my knapsack can carry big kilograms. Everything is in kilograms inside like metric system. So, well, this is our generic problem. Well, this is for 5 objects. But it can be, for any object, n object or anything. And then we discussed about how to solve it. We talked in class that if we don't have this constraint, which is the 0, 1 constraint, there was a way to solve it. What was it? Yeah, so it said that if xj's are between 0, 1, we can solve it using LP, but there was even an easier way of solving it. You just had to order them in some sense and then pick them. What was that order? Yeah. So it was the order of Cj over Aj. Basically, if the value is in dollar, it seems that everything is measured in money, so we do it in dollar. And the thing is kilogram, so you rank them by dollar over kilogram, which means that which one is giving you more money for same amount. And then you start picking the most valuable one. You first pick the diamonds, then you pick the rubies, then you pick the jades, and then you end up picking the pebbles at the end. So, and then you start filling this, up to end, and at some point, so you start picking something until you cannot pick more than that. You have picked all your diamonds. And then step by step. And the last one that you're going to pick, you see that after you pick a certain amount of it, then this thing is filled. This thing is full. You cannot pick more. So we realized that this would be solved even without this constraint, having that sum of xj's would be equal to 1. Then one of them would be perhaps fractional. If you're lucky, even that one is not fractional. And then the rest would be 0. That was when this guy was not there. But was there. This guy was not there. Now, our problem is not in that setting. In our setting, you can only pick 1 or nothing of something. Then, obviously, that method wouldn't work. Because think of it like this. Assume that our b is equal to 2. And our first object has the value of, let's say, $1,000. And its weight is equal to 1.5. And my second object has value of 999. But no, that's too much. It has the value of, let's say, 600. And it has weight of, I'm trying to make good numbers. What's 1,000 divided by?
No, just one. Another one.
Yeah, that's it. But what's this one divided by this? 6 something. So let's make this 1 point, just 1. Maybe even just 1 would work. Just 1 would work. Yeah, just 1 would work. And C2 would be 501. I just want to make them different. Let's make this 4, 9. 501 here. And 500 here. Okay, I just wanted to make it different so that I can rank them. Okay, so if we rank them by the method that we had, this guy would be 660 something, this guy would be 501, and this guy would be 500. So we would pick the first one, but then we cannot pick anything else, and we will end up with having this value. But obviously the best solution is to pick these two, which gives you a value of 1,001, which is more than a value of 1,000. So we will see that, in such a very easy case, only 3 objects, our method would fail if we have to use binary variables. So we have to do it in a different way. There is one trivial way that anybody would give if they have passed the first grade, maybe even not that. So what would be that way? Yeah. We can just check all the combinations, How many combinations you would have? You have n items, okay? You have n items. So let's look at our items. I'm just going to stick to my example, 5 items. And each of them can either be in the knapsack or not in the knapsack. So each of them would have two possibilities. So each of these guys has 2 possibilities. There would be how many possibilities? 2 to the power of 5 possibilities. So you can just look at these 2 to the power of cases. Just pick this one, don't pick that one. For example, this would be one case. Look at all the cases. First, sort them out, those that are feasible. Then among the feasibles, look at the one which has the highest value. That's your answer. So this would be one way to count everything in a very naive way. But then we want to come up with another way to count it. And let's think of it the way that, let's think of it this way. We want to solve a knapsack problem with n objects. If many of you have done any coding in your life, which I assume some of you have done something, you might have heard of something called recursive methods. Okay. So what are recursive methods? They said that if you want to do something for n, if you know how to do it for n minus 1, and if you know how to get one step ahead, then you're going to be fine. Because you know how to do it for 0, for example, then because you know it for 0 and you know how to go one step ahead, you would be able to do it for 1. And when you would do it for 1, you can do it for 2, go a step ahead. So I'm going to look at a simpler problem. I'm not going to look at a problem with 5 objects. I'm going to find a method that if I know the solution for 4 objects, I can just go one step ahead and find it for 5 objects. And then I'm going to start from the first object, the only one. this one. I assume nothing is there, and I'm going to solve a problem of knapsack with only one object. So there would be only two choices, either to put it or not to put it. And I'm going to find a method that, knowing that, I can find the solution of the two object problem easy. And then knowing that, I should be able to solve the three object problem easily and go ahead. So I'm just going to find a method like that. So instead of looking at this problem, I'm going to look at this problem. Maximize summation j over 1 to r of cj xj, given that aj xj is less than or equal to b, and xj is a 0, 1 variable. And r is a number between 1 to n. Okay. So I'm going to solve this problem for r equals to 1, and then knowing the solution for this, I'm going to solve it for r equals to 2. Then knowing the solution for this, I'm going to solve it for r equals to 3 up to r equals to n. And I think everybody agrees that solving it for r equals to 1 is not a hard problem. It would be maximize c1 x1 given a1 x1 is less than or equal to b, and given x1 is either 0 or 1. This is not a hard problem. One variable. You just have to check what? Two cases. You just have to check. If it fits in the bag, put it there, done. If it doesn't fit in the bag, 0. So the answer is either 0 or C1, and you know everything nicely. So if I just find a method of going from r equals to x to r equals to x plus 1 in an easy way, then I have found the easy method to solve this problem, which I really don't know how to solve. Because I know to solve the first one easily, and I have found a method to go this step easily. Then the whole thing would be easy. Now, there is one problem. Even this one is not easy for me to solve. Okay, even this one is hard for me to solve. So I'm going to even parameterize another concept here, which would be the b. Instead of looking at b, I'm just going to look at lambda. And lambda is also any number between 0 to b. Okay, I even don't know how to solve it for b. Okay, I assume that I have a knapsack which I want to put only one object in it. And somebody tells me that the knapsack has capacity of 10. I don't know how to solve it. I'm going to look at the knapsack that I want to put one object in it, and only has capacity of 1. I know how to solve this one. Then I'm going to go to capacity 2. Then I'm going to go to capacity 3, 4, up to 10 to solve it. So basically, I parameterize two objects. This might look a little bit abstract. Don't worry. When we solve the problem, it's going to be very easy. So I'm going to look at this problem instead of the original problem, and then solve it for all lambdas and solve it for all r's. And then when lambda equals to b and r equals to n, this is my problem here. Okay? And then we'll find a method that it's easy to solve those problems so that finally you can solve this one easily. That's going to be the whole trick. So just to, some notation, we call this value z, as always. And this one we'll call it fr lambda. So fr lambda would refer to a problem of a knapsack which we want to put r items in it, and we have capacity of lambda. When r equals to n and lambda equals to b, this would be our original problem. Okay? This is the whole story that we are going to go through. Now we have to do some real arguments to develop this machinery that we need to go from here to here. And after we develop that, we are done. You'll see that it's a very easy thing. Now, let's see how we want to do it. Okay. Assume that x star r is the optimal solution for the problem fr lambda. Okay? For all lambdas. Lambda is not really important in our case. Now, let's call it, this is the problem. I have to look at this so that I don't say something nonsense, really. Okay. So this is the solution for FR lambda. Now, what is X star R? X star R is a, let's say, X star 4 in our problem. Is a vector which tells you which one of these 4 items to put there or not to put there. So it would be a vector which looks like this. 1, 0, 1, 0. Bless you. So first item, second item, third item, and fourth item. So X star R would have R elements. Okay, now, only look at the last element. How many cases, how many values can it have? 2. So what would be the value of this one? It's either 0 or 1. Okay, so if we look at X star R, what kind of notation do we use here? We really don't use any kind of notation here. So I'm going to say T. So, X star R, I need to put another index somewhere. Okay, I'm going to put it here, R. So this means the rth item of X star R. So it would be either 0. Let me make my notation clearer. I'm going to call this guy X star. And by X star R, I would refer to the rth item. Okay? So just, don't make too many indices. So the last item would either be 0 or 1. Now, if the last item is equal to 0, let's see what it means. It means that if you look at by the indices that we have here, we can look at this problem So we looked at problem FR lambda, and we realized that X star R equals to 0. It means that when we had 4 items and we maximized our solution, the last item was not put here. Okay, this would mean that if we look at the problem with 3 items and the same capacity, the value of the objective would be equal in these 2 cases. This is the most crucial observation that we have to make here. So let's see what it means. I'm saying that I solved the problem for these 4, and it turned out that it told me, we don't know anything about this. It told me, don't put this there. So basically, the optimal solution was a combination of these 3, which was put here. Now I'm saying that, so the value that we got here should be equal to the value if we just optimized over these 3. Because this one was not even put there, even when we introduced it into our problem. Is this clear? Yes or no?
Can you repeat it?
Okay. Yes, why not? So let's think of it like this. I'm just saying we had a problem, maximize 10x1 plus 20x2 plus x3, given that 2x1 plus 3x2 plus 5x3 is less than or equal to 5. Okay? This was my problem, and everything is binary. Okay. Now, the solution to this guy, when you solve it, it turns out to be what? It's 1, 1, 0. Okay, I just showed some arbitrarily big numbers to make it clear that, these 2 have a lot of value, you put them there, this one. So this would be the optimal solution, 1, 1, 0. Okay. Now I'm saying that when this guy was not there in the optimal solution, if I had solved this other problem, maximize 10x1 plus 2x2, given that 2x1 plus 3x2 is less than or equal to 5, 20. Yes. I'm just saying that which the optimal solution would be 1, 1. I'm saying the value of objective here and the value of objective here would be equal. Because this one is 0 here, it's as if it's not here. It didn't contribute anything to constraints. It's not going to contribute anything to constraints here either. So the observation is, if you solve FR of lambda, which means that you want to put R items in a knapsack with capacity lambda, if it turns out that item, the last item is equal to 0, meaning that you don't put the last item there, the objective value would be equal to the objective value of solving the problem without that item, but with the same capacity. Okay? This is exactly saying this thing in abstract mathematical notation. Is it clear? Yes? No? A little. Okay, yes. Now, having this observation, so we know that if x star r equals to 0, fr of lambda equals fr minus 1 of lambda. So in that big picture that I was talking about, I'm trying to find a relation between problem with r item and problem with r minus 1 item. Okay? And then I would start solving problems of 1 item and then do that for 2 item, 3 item, because I'm just trying to find an easy relation between them. Now, if x star of r equals to 1, it means that I'm putting that object there. Can anybody guess what would be the relation between these two values now? Okay, greater. Yeah, one of them would be greater than the other one. That's correct. But we can find a equality relation like what we found there. Yes?
Take lambda minus the weight of
Okay. And you add something to the objective too. The value that it contributes. You're correct. So let's see what happened here. So when x star turns out to be 1, it means that our problem looks like this. This was 100x3, and this was x2. This is 5x2. This is 2x3. Okay? I'm just writing a new problem first, giving it a concrete idea. Okay. Now, let's see what it means. Now, when you solve this problem this time, the optimal solution would be 1, 0, 1. Am I correct? Yes. So it would be 1, 0, 1. And the optimal solution would be here would be 1, 0. Yes? Okay. So the optimal solution here would be 1, 0. Here it would be 1, 0, 1. Now, look at the objective function here. It would be what? 10 plus 100. Here it would be 10. Okay. Now, from a knapsack point of view, let's see what happened. I solved this problem, and in the optimal solution, this guy was here, was put here. Now, I'm saying that the value that you get, and some of these guys, which we really don't know which ones, are here. Some of these are here, but we know that this one was put here. Okay. I'm saying that this would give me a value. I call it V. So the value of this optimization problem with 4 items would be V. Now, I'm saying that this value would be equal to, as if I have a knapsack which has capacity, I have a knapsack which has this capacity, okay, and only has these items. So I have a knapsack with this red capacity and these red items. I optimize it and add the value of this guy to it. It would be as if I have a knapsack with big capacity, put this one there, and then optimize over everything. Do you see the point? It's not that, I know it's not as easy as the previous one. Let me write it down and explain a little bit more on it. Maybe here the mathematical notation would help. I'm saying that f r of lambda, r items with capacity lambda, if the r item is put there, is equal to value of that item plus solving the optimization problem with one less item and capacity minus capacity of that item that I put there. Okay? So it's like saying that I want to put my sandwich and orange and water in my bag, and I want to optimize my solution. I solve it. I see that I have to put the water there, and my knapsack let's say, had 2 compartments. Now I'm saying it's like just assuming my knapsack had 1 compartment, and I only had the orange and the sandwich. I optimize over it and add the water to it. This would be the value as if I had 2 compartments and had it all 3 items. Why? Because I know the water would end up being there. That's the idea. So I'm just saying, let me draw this picture in a better way. Might make sense. I'm saying I had this capacity, and I know that 1 item was put here, and some items were put here. I'm saying this capacity, this value would be equal to just optimizing over those some items and adding the value of this guy to it. Okay? So I'm saying if, this if is a very big if the last item is put there, the optimal value would be equal as if I don't have that item, I have a knapsack with a capacity which is the previous capacity minus the amount that that item took. I optimize over that and add the value of that odd item to it. These 2 values would be equal. Is it clear now? Yes or no?
Yes.
Wow, that was a good yes. I hope that you meant it. So having these 2, it's enough to solve all the problems of this type. Done. Yes?
Can there never be a situation in which the optimal solution for 2 gets completely changed? Like in this, we're assuming that if it is 1, 0, there will also be 1, 0 for 3 items. If it becomes 0, 0 and 2.
Oh, you are saying that, okay. No.
0, 0 and 1, sorry.
Sorry. There is a problem here. My mistake. 5 minus 2 equals 3. Okay, now. I had to deduct the capacity of this guy from here. That's lambda minus AR. Okay? So I'm just saying that I had this optimization problem over 3 items. I solved it. I realized that the third one would be there, which gives me a value of 100. I'm just telling you, if you want the optimal value, forget about everything. Just solve it with these 2 and these 2 constraints. Forget this guy. And also, since you're going to put this guy there, deduct whatever it takes from the knapsack. Make this 5 equal to 3. So solve a knapsack with capacity 3 and only 2 items. Find whatever its value is, add 100 on top of it, and then you're fine. This all is because I know in the optimal solution of this one, this guy will be there. Okay? Yes or no? Yes, no? Yes. Okay. Now, having just this machinery, we are going to solve one of these problems. And I think after solving a numerical example, you will see that it's not a big deal. It's very easy to deal with. Now, let's look at this example. Okay, now I have a good, whenever I ask you if you have learned, you got it or not, I really don't rely whatever you tell me because you never tell me the correct thing. But when you start talking, I know that you understood what I'm saying. So it's a good sign whenever I hear talking from back, it's good. Whenever I say something new, everybody listens. So at least I have a good measure of checking here. Now, so the problem that we are going to solve is this. Maximize 10x1 plus 7x2 plus 25x3 plus 24x4. Okay. And our constraint is 2x1 plus 1x2 plus 6x3 plus 5x4 less than equal to 7. And xi's are binary for all. Okay. This is our problem. I'm gonna need everything on the blackboard, I think. Yes. I nearly need everything on the blackboard. Now we are gonna make a table and start filling this table in, and after it's done, you would see how we work. So, Why did I say 6 here? This should be 7. Okay. Sorry. So, I told you that I'm going to solve this problem for all values of r and all values of lambda. So my r is 7, my lambda is 4. So I need a table of 8 by 4, 0 to 7 and 1 to 4, and I have to fill all the blanks in it. So the first thing is to draw this table. People in the back, can you see this one? Okay, good. F1, F2, F3, F4. Okay. Okay, so I'm going to fill all the empty places in this problem. Now, let's do it step by step. The first one that we want to find is f1 of 0. So what does f1 of 0 means? It means that you want to put one item, the first item. Maximize 10x1. Given that 2x1 is less than or equal to, what's the capacity? 0. And x1 is either 0 or 1. So what's the optimal solution here? 0. So this guy is 0. And now I add a little thing to the right side of this table. And it's not a really big deal. After I explain what it is, I think it's going to be crystal clear why I need it. And don't worry even if you don't see it back there. This part is not really crucial. I call it P1, P2, P3, and P4. So whenever for this one, I chose the object here, I would put a 1. If I didn't choose the object, I would put a 0. So in F1, 0, I'm talking about object 1. I didn't choose it. X1 turned out to be 0. So I also put a 0 here. Okay? So I didn't choose anything, and I ended up having the value of 0. Now, since you're all, intelligent people, it's obvious that for 1, this is going to be also 0. So another 0 put here. Now, for 2, the answer is going to change. What is going to be the answer for 2? 1. So you would put one item here. Sorry, let's make this 0 and 0. So you're going to choose the item. So item is chosen. And what will be the value? 10. So you're going to have 10 units of whatever it is that you're maximizing. 10. Okay? Now, trivially, if this number ends up to be 3, 4, up to 7, you're going to always end up choosing this one. And you're going to always have value of 10. This is a small difference. When you look at this problem as an integer problem, not a binary problem, you might be able to choose it 2 or 3 times. So a method would be a little bit different. This is going to only work for binary ones.
How did you get the second one?
The second one? 1?
Yeah.
I just said that I'm solving f1 of 1. Maximize 10x1 given that 2x1 is less than 1 and x1 is either 0 or 1. So the only feasible answer is 0.
Sure.
Okay?
For integer problems, this won't work.
For integer problems, it's a little bit harder. The same method with a little bit modification would work. We're not going to worry about it. So now, I just fill this fast. 3 is equal to 10. 4 is equal to 10. 5 is equal to 10. And in all of them, the item is chosen. Okay? Is it clear? Okay. Now here the nice idea kicks in. Now we want to calculate F2. Okay. When you want to calculate F2, you have two choices. You have to, let me just make sure you might missing. Okay. You have to make a decision. Now you are looking at only F2. Assume you don't know the solution for F1. But it's like this. Let me make a analogy here. You have a knapsack with two items in it, and you want to maximize your capacity, your value. You can look at your decision sequentially. The first decision is, shall I choose item 2 or not? And after you decided, you can go on item 1 and think, shall I choose item 1 or not? And then finish your decision. Now, writing it in mathematical terms, this is something that we're going to need it and use it. If you are staying at stage R and you're looking at capacity lambda, you have to choose. You have to decide. Forget this, what it means. You have to decide if you want to put the art item there or you don't want to put it. So, you have to, let me write it down and then I will explain it. I can... Okay. This is where this thing comes into play. Let's just give you a second to write it down because I want to explain it and I want to have everybody's attention. So, what I'm saying is this. At the art stage, I'm going to do this. I'm going to look at the art item and say this thing to myself, that is it better that I forget about this R item, assume it's not, this is R minus 1, is R. Is R minus 1, sorry. I made a mistake. No, it's, oh. This is R minus 1. Yes, sorry, R minus 1. Okay, let me just make sure if I wrote it correctly. Yeah, this is R minus 1. Sorry, I was writing it for something else. That was something else. Now, okay. So, now what I'm saying is this. In the art stage, looking at the art item, and I don't know what's going to happen before me at all. There are R minus 1 items that I have to decide about them later. I don't worry now. I say that, okay, either the best solution is one of these two. There's no way out. Either the best solution comes from not putting this guy there and solving a problem with the other items and the same capacity, or the best solution is putting this guy there and solving the problem for the other items with a smaller capacity. There are two choices that I can make. I either put this guy there, I either don't put this guy there, and just look at the problem with, instead of 10 items, 9 items with the same capacity, solve it. Either this is the best solution, meaning either xr equals to 0, or either xr equals to 1, which means that I put this item there, I get the value of CR, and then solve a problem, solve a knapsack with a smaller capacity and with 1 item less. So basically I'm saying either the solution is xr equals to 0 or xn equals to 1. And I have to choose the maximum. This is the step that we're going to use this knowledge that we got there. So at step 2, which I'm sitting here, I'm going to do this. I'm going to say, okay, let me erase this one. I really don't need this anymore. I'm going to say, I want to calculate F2 of 0. Well, F2 of 0 is easy to calculate, so let's just do it. F2 of 0 would be maximize 10x1 plus 7x2, 2x1 plus 1x2 is less than or equal to 0 given xi binary. So when I'm going to solve this one, just looking at F2, I would say don't put it there. It's not going to make any sense. So I put nothing there. Sorry, I put nothing there. And the value of it would be f2 of 0 would be equal to maximizing f1 of 0, comma. Okay, that's it. Basically, I cannot put the other one. It's not feasible. Okay? So when you have f2 of 0, it means that you only are talking about the second item. Okay? You cannot put it there. It's not feasible. So you just don't put it there. It would be end up just going one stage behind. Yeah, this what I'm saying is this. I'm saying that I have no capacity left. I have two items. But I'm looking at them sequentially. First, I look at the second item. I have no capacity. I don't put it there. Then I go at the first item. I still have no capacity. I don't put it there. Okay? It's just like, instead of looking at it in one step and saying that I have two items, try to think in stages. That's all I'm saying. You have two items, you have zero capacity left. First look at the second item. Can you put it there? No. So it's not put there. The first item, can you put it there? No. So it's not there. So thinking of it in a sequential way, I'm saying that the second item, can I put it there? No. So this one is not even feasible. The only thing left is this one. So the value of f2 of 0 would be maximum of just one value, which would be f1 of 0. And f1 of 0, I have calculated it beforehand. It's 0. Okay? Good. The 0 one is trivial. But the first one is not trivial anymore. Now, when I look at f2 of 1, I'm solving this problem. Now this is not trivial anymore. And this is where our solutions in the first column would help us. I'm saying I'm solving the two item problem with one capacity left. So I can do two things. The first way is not put this item there and go and solve a knapsack with one item and 1 unit of capacity, which means f1 of 1. Or I say I put this item there, I choose the second item, so I get its value, which is 7, and go to the stage before without any capacity left, which is f1 of 1 minus 1, which equals to 0. So now I have to decide if I want to do this one or if I want to get this one. This is the crucial step. So, but what is f1 of 1? f1 of 1 means you have 1 unit of capacity and you have to choose item 1 or not. But you cannot even choose item 1. Well, you don't look at this thing here. Its value is 0. So this is 0. This is 7 plus, this is f1 of 0. f1 of 0 is 0. So this ends up to be 7. So maximizing f2 of 1 with maximizing between 0 and 7, its value would be 7. So I put a 7 here. And did I choose the second item or not? I chose the second item. So I put a 1 here. Okay, let me reiterate what I said, because this is the only time, because the rest of the table is just filled repeating this thing over and over and over. So let's see what we did. Let's do it for the 2 item case and see what happens. So for the 2 unit of capacity. Okay. You really don't need to write any more calculations from now on. It's just repeating the same old calculation. Now, I'm looking at a knapsack which has 2 kilograms capacity left, and I have 2 items to choose which one I want to put there. So first I look at the second item, and I say I can choose not to put it there and solve a knapsack problem with the only item left and the 2 kilograms of capacity, none of it used. Or I can choose to put this item there, get a value of 7, but then now my capacity would decrease. My capacity would be from 2, which was the original capacity. I'm going to put this guy in, so I'm using 1 unit of capacity, and solve the problem with 1 item less. So either I don't put it there, I keep my capacity, solve the problem with 1 less item, or I put it there, I lose 1 unit of capacity, and I solve the problem with 1 unit less. So this would be 1. So this would be f1 of 1. Now, f1 of 1, f1 of 1 is 0. It means that if I go to the first stage with 1 unit of capacity, I cannot put anything there. I wouldn't gain anything. So this would give me 7. If I go to the first item with 2 units of capacity, f1 of 2, I can put the first item there and get 10 units of value. So the maximum between these two would be 10. So it's going to tell me, although you have the choice of putting this item there, don't put it there. Go to the first item and put the first item there, because it's going to give you more value. So the value here would be 10. And did I choose to put the item there or no? Did I put the item there or didn't I? I didn't put the item there. So I put a 0 there. So let's see what I did. Can somebody walk me through what I did? From so many yeses, one of them. Please? I'm going to help you, so don't worry. I have to choose then, then it's bad. Somebody, or let's say somebody does the next step for me. Good. Don't tell me the answer. We're going to walk through it. Okay, good. So, we are going to solve this. But that was good. So, we are going to solve this. So, the next item is F2 of 3. So, what should I do? You know. How did you get 17? You know it. Go ahead.
Okay, I just do it by plugging in 3 on the constant.
Okay. Okay, don't do it that way. You can always remember, the whole idea is not to solve this one. We don't want to solve it.
You just say F1 of 3.
Yeah, well, even forget this one. The first thing that we can make 2 decisions. What's the first decision?
F1 of 10.
Oh, no, just in words. Forget this. We can either... No. I just want you to say me in words. You have 2 objects. You either take it or not take it. So if you don't take it, you go to the first stage with how much capacity? The same capacity. So you go to the stage before with the same capacity. This is as if you say x2 equals to 0. You didn't choose it. Okay? Or you do what? You take it. But if you take it, what would be the value of your objective? You would put this 7 there. You have it in your hands. And now you go to the stage before you with a little bit less capacity. Meaning, you go to the stage before, you had 3 units of capacity, but you used 1 unit of it. So this would turn out to be 2. So this is F1 of 2. Now, F1 of 2, you have calculated beforehand, it's 10. So this whole thing would be 17. F1 of 3 would be 10. So it's telling you, choose the item, and also you will go to the stage behind and also choose the other one too, because you have enough capacity to choose both of them. 17. And this is 17. And we chose the item. Okay. Now, does this really make any sense?
We chose which item? We chose the F.
Yeah, remember, when you are in the stage 2, F2, you are only talking about choosing the second item. So let's put it like, that was a good question, in fact. We have, for some reason, after doing calculations on stage 3 and 4, which we haven't done yet, we came to stage 2. Now we have to decide for the second item. And we have 3 units of capacity left. What this table is telling you is choose that item. You choose it, and then you go to the first stage and look at it later. We're going to see how we read this table in a second. First, we are trying to fill this table. Okay? Now, is this thing making any sense to you? Okay, good. Yes?
The final solution is going to be the final.
Okay, now we're going to go to, okay, now We really don't want to do all these calculations again. So I hope that by now you should be able to fill this table yourself. Okay, I'm going to write down the numbers for you, but try to do it yourself, please. Okay, this is not going to take you that long, but try to fill it yourself later to just see how I got these numbers. So this table turns out to be this. We're going to do one more of them, and then I'm going to stop doing it. What's happening there? Okay. I have just done the calculations and I have come to this stage. Now I just want to fill this place. So I want somebody to fill it for me. Okay, let me just erase everything that we have here because we really don't need this anymore. Okay. Who wants to fill this? Come on. Yeah. No, don't give me the number, okay? So, first of all, what are we calculating? F of what?
F4 of 5.
F4 of 5. Which means that we are deciding on the fourth item having 5 units of capacity. Okay. So, we are maximizing over what?
F3 of 5.
F3 of 5, which means what? No, which means what?
That we are not taking the
Yeah, which means that we didn't take the item, so we went to the third stage with the same capacity, and what's the other one?
24 plus
24. It means that you chose the item. Sorry, this is 0. And then you went to the stage before with how much capacity?
F3 of 5 minus 5.
Good. F3, 5 minus 5. Which gives you 0, F3 of 0. And this is F3 of 0. Now, what's the value of F3 of 5? F3 of 5 is 17. The value of F3 of 0 is 0. 24. So you have to choose between 24 and 17. Obviously choose 24. And to make the decision of 24, it means that you choose the item. Yes?
In the row above that,
17? Okay.
F3 of 4 minus 5, F3 of negative 4.
Oh, no. Whenever you cannot put the item, that's okay. Good question. That's good question. So remember in the first stage, when I was looking at F2 of 0, I just wrote down this is maximum of F1 of 0. But the second item, I even didn't write it down. Why? Because it was not feasible. If I had put the second item, it would have been 0 minus 1, which equals minus 1. So when this second item becomes infeasible, you just don't write it. Basically, you have no choice. It's like this. You have a knapsack which can carry 10 kilograms, and you have 10 items left, 5 items left to choose. The fifth item is 11 kilograms. You cannot even choose it. You go to the fourth item without any decision. So here, when you are looking at F4 of 4, it means that your knapsack can carry 4 kilograms, and you're deciding on the fourth item. But the fourth item is already weighs more than 4 kilograms. So you just have to forget about it and go one step behind. Yes?
Why is speed 3 as 6 and 7?
Why this turned out to be 1? Because it was chosen. Yeah, we will fill one of it. Let me just fill. Yeah, let me fill it. Look at...
P1 is 1 and P2 is 1.
Huh?
P1 is 1 and P2 is 1 and P3 is 3.
You are talking about this one, yes? Let me solve it.
So how does this satisfy this constraint?
No. I didn't tell you how to read this. You don't know how to read this yet. Okay, you just know that. Okay. Don't jump too much. We only know one step of. We know one interpretation of this table. This table says if you end up at a stage F2 and 3, you're going to choose it. That's all it means. It's not giving you the optimal solution yet. Don't worry. Okay? I haven't told you how to read this table yet. We are just filling it yet. Okay, so after you fill this table with the procedure that I told you, it would look like this. No, you don't have to choose 1, 2, and 3. No. I didn't tell you how to read this table, okay? You should be able by now to fill in this table. Okay, now, let's see what this table means after being filled. And filling it was totally a mechanical procedure. Just doing this repeatedly. Now, forget about this part of table at all. Forget about it, okay? Now, let's see how we have to read this table. One thing that we know is that all the values here are feasible. You can choose one of them. You can attain this value by a mixture, but we don't know by which mixture yet. How do you know that you can attain this value by some mixture of it? Because you just got them doing this procedure, which was choosing. Basically, you just enumerated the different cases and filled in this table. So the maximum value here would be the maximizer of your objective function. Basically, this would be the maximum value that you can get. So z, which would be equal to f4 of 7, which would be equal to 34. And f4 of 7, it means that you have 4 items, 7 units of capacity. It's your original problem. Okay. Basically, it's the number down there always. Now, let's see how we can attain this 34. This is the important thing that we have not answered yet. This is when we are starting to read the table to our right. So, we start looking at our knapsack, haven't chosen anything yet. We have 4 items, an empty knapsack. So we are at f4 of 7. What's the decision at f4 of 7? The decision at f4 of 7 is choose the item. So x4 is chosen. Okay? Now, when x4 is chosen, if this is your optimal vector, x star, you don't know anything, you just know that this one should be there. Now, when you choose it, what's the stage that you're going to go? F3 of 7 minus 5. 5 comes because this. 2. So you go to a stage F3 of 2. So on the stage when you have to choose this guy, you are here, actually. Okay? Now, what's the decision that you have to make here? 0. So it says, don't choose this item. You wouldn't choose the third item. Okay? Now, after the third stage that you had 2 units of capacity, you didn't choose the third item. So which stage do you go to? F2 of 2. In the stage F2 of 2, it's going to tell you, don't choose anything. So you wouldn't choose anything still. It would be 0. Okay? And after not choosing anything here, what's the stage that you're going to go? F1 of 2. Now, I'm going to explain what's happening here, don't worry. In the stage F1 of 2, it tells you choose the item. So you choose the item. And this would be your optimal vector. If you check it, you're going to choose the first item, last item. 2 plus 5 less than or equal to 7 is feasible. And the value that you get is 10 plus 24, which is 34. Which is the objective? 34. Okay? So this is how you read this table. Okay.
How do you get from P3 and 6 to 1 over 10?
From here to here?
The column of P3.
How did I choose it?
6.
You mean this one, for example? Okay, I'm going to tell you how we did it. Okay, just give me a second. Let me explain what I want, then we're going to do that one again. So let's see what we did in big picture. Let's see what we did in big picture. We said that we have a knapsack which has 4 items out there, 7 units of capacity. What should I do? I said look at them stage by stage. Look at the 4th item first. Now this table tells me if you have 4 items left and 7, you can attain the capacity of 34, And the decision is you have to put that one there. So you put that one there, and when you put that one there, you're going to go to another knapsack which only has 3 items left and only 2 units of capacity. But 3 items and 2 units of capacity tells you don't choose anything. You don't choose anything. You go to the one stage before that, which tells you 2 items and 2 units of capacity. But still, you don't choose anything, and you go to the first item. Now, this whole thing, this whole argument, is based on something called principle of optimality, which I don't know if Professor Hanger would talk about it or not, but it's a very easy thing to talk about. Assume that you want to go from here. Which street do you live in? 123. So you want to go from 120 to 123. Okay. And assume this is your home, this is here. Now, this is the best path to go there for some reason. There are some streets here, there are some obstacles. This is the shortest path to go there. Okay. Now, this whole thing is based on if the shortest path from here to here passes through this line, okay, then this part should be okay. Maybe I should use different colors. So I'm going from A to B, and it's passing through C. So this whole argument is saying that if the shortest from A to B passes through C, then AC is the shortest path from A to C. You see what I'm saying? If from going here to Columbus Circle, the shortest path goes through Morningside Park, then the shortest path from here to Morningside Park is that part that you're going on the Columbus Circle path. Otherwise, if there was a shortest path, you would take this one, and then the shortest path to B would be this one, not the big one. Do you see the point or no? This is very crucial. If your shortest path from New York to Los Angeles passes through Austin, then that New York-Austin part is the shortest path to Austin itself. Otherwise, you can take I think there's no otherwise. I think it would be less confusing if I do that. So I'm saying for the shortest path from New York to Los Angeles, you have to pass through Austin. Then for the shortest path to Austin, just go that part, and it would be the shortest path itself. Now, I'm saying if the best path, which is going to maximize your capacity to this guy, is going to pass through these capacities, this itself would be the best capacity. Okay, I said it in really bad words. I'm saying if you want to gain the maximum capacity, maximum value, when you have 7 units of capacity and 4 items, if to go there you have to pass through these paths, these themselves are the optimums. So I start by calculating the optimums for this one until I get here, and then I track back. All these items that you chose were this maximum. Each of these items were the solution of a maximization problem, which we always wrote down, but we never solved. We just used the data of before to use that to solve that one. So all of these small ones, all these numbers are optimization solutions for 3 items, 4 capacity. Basically here you have the solution to 8 multiplied by 4, 32 optimization problems. You have the solution to 32 optimization problems. You can easily solve this problem now. You are easily able to solve this problem. This is nothing more than F3. Well, this is bad. Let's make it 2 third numbers are different. So this is just F3 of 2. This is just this problem. This is just this optimization problem. Nothing more than that. So you have solved all the intermediate optimization problems, but you never solve them explicitly. You just use the data from the previous ones to add the new ones. And then you ended up here, and then you backtracked through the method that I told you. We said 34, choose the item. When you choose it, you end up here. Here, don't choose it. You end up here. Don't choose it. You end up here. You choose it. That's it. Now, you got it? Okay. Now, to calculate that table, we only use this data. Basically, we always said that to maximize this value, it's either better to take the item or not to take the item or take the item. If you don't take the item, it's as if you solve a knapsack problem with 1 fewer item, same capacity, or it's better to choose the item and solve a knapsack problem but with 1 fewer capacity, one fewer item, and a smaller capacity. We reiterated this, filled this table, and then read it. Yeah.
Now, does this work if the coefficients of the objective function are non-integer?
Yeah. If the coefficients are non-integer, it's gonna work. But then you will have a lot of different numbers here. Because what is this number? This is just the remaining capacity. So you have to end up having f1 of lambda, let's say 2.3. So let's say, that's a good question in fact. If instead of 2, you had 2.1 here, there are different ways to solve it, okay? But one way to do it is just multiply everything by 10. Now everything is integer and you can solve it. So it's better to do it that way. Just make everything big enough, multiply by, so that everything is integer. If they are not integer, it's harder to handle it. Because then writing this table wouldn't be that easy. We solved the knapsack binary problem with this method now. You can solve knapsack integer problem with this method. You can solve non-knapsack. You can solve non-knapsack problems. Basically, any problem, optimization problem, which you can break it into stages and states. Meaning, no, as many constraints as you want. Okay? Any optimization problem that you can look at the decision in stages. And in each stage, you can define a set of states. So in the stage 4, we can be either in 0 capacity stage, 1 unit capacity, or 7 unit capacity stage. So these would be different states. These would be different stages. Any optimization problem that you can break it down into stages and states, you can solve with this using this method, which we call it dynamic programming. It's a very useful method. A lot of problems are solved this way. And as you might guess, the problem with it would be computational time problem. It normally, where it breaks down is where you have to do a lot of computations. That's the problem with this method. But in a lot of cases, the computations are very easy and straightforward, like this one, so you can do it fast. Sometimes it might be hard to do it. If you know what a network flow problem is, a network flow problem can be solved this way too. Or any problem that you can just break it into stages. Question? We'll talk about it in class. Professor Anger is going to teach this in more detail tomorrow. So this is just an introduction to it. Now, I want to do a short review of the active set methods, which you might find it useful. Just to see a big picture of what active set methods is. We are not going to do one stage. We are just going to look at the big picture. Now, okay. What you had in active set methods, you had the mechanics of how going through. Hello, nobody's forced to stay in this class. You can always leave. So, So let's say what active set methods do and what we were trying to do with them. We started looking at nonlinear programs, and we started looking at linear programs. Then we looked at their geometry. We saw that all the solutions happen on the corner points. So if we only go and search the corner points, we are fine. So we found a method which goes on the corner points, checks them, and finds the best one. Then we looked at the nonlinear programs. And the problem with nonlinear programs was, if you looked at it in general, you had no idea what to do with it. Because your function could be any weird function. It can be non-continuous. It can be non-differential. It can be any weird thing. Your set can be any weird thing. Basically, you cannot solve it. Then we started saying that, okay, instead of looking at those problems that we cannot handle, let's look at a smaller set. So in a set of the nonlinear problems, which was really big, nonlinear, we said, okay, let's look at a very small part of it. And we called it convex problems. Okay. So what were the convex problems? Convex problems were problems that the set that we were optimizing over, so the ST part, which said X is in a set S, we said the set S should be convex. Okay. And then we also said that if you are minimizing or maximizing a function, If you are minimizing it, it should be convex. If you are maximizing it, it should be concave. So we defined a set of nonlinear problems, in fact, it's not even this big, it's this big, maybe even smaller, that we cannot solve this. Okay, we forget about them. So look at this small set. If set S is convex, and these F's are either convex or convex depending on if it's minimum or maximum, let's forget even that maximum and just say minimum. And then this guy has to be convex. Then we said we call these convex programs. And we see that if we can solve them or not. Then convex. Even for these to solve, we really didn't learn a method to solve these guys. Okay? Look at an example that I'm going to give you. Let's have this example. Some people have asked me this in the past few days, so they might have seen this example. Assume that your feasible set is this set. So this is your feasible set. Above this line, left of this guy, right of this guy, left of below and below this. Okay, so the feasible set would look like this. In fact, that weird constraint up there, which might be, I don't know, sine of x plus 10, okay, something like that. This even doesn't play any role. You can just drop it and look at this. Obviously, this set is a convex set. It's a rectangle, okay? But you have this weird, very weird looking constraint there. Now, this is a two-dimensional case. You draw it. You see that this weird constraint doesn't play any role. You forget about it. You just look at this constraint and solve it. But when it's a, I don't know, 20-dimensional problem, you cannot really draw it and check if this constraint is playing any role or not. Okay. So even if your set might be convex set, you might have some weird functions happening somewhere which you have no idea what they play the role. And if there is such a weird constraint there, since you really cannot check if it's active, not active, or anything, you even don't know how to solve those problems. So this convex sets, these convex programs, which are really nice, we still don't know how to solve this even. We know one nice characteristic about them though. We know that if we find a local minimum or a local maximum there, it would be a global or a global maximum. We know that one. That's something good that some guy proved for us at some point. But we need a method to find that local minimum or maximum. Now, our method, the one that we know, even wouldn't work in this case. Unfortunately, even in this case, that you have such a weird-looking function, although the set is convex, although the function is convex, you still don't know how to solve it. So we even refined this thing and said, forget it, we cannot even solve that. We're going to look at a smaller subset of it. And in this smaller subset, we said that if our functions are like this, or this, or this, well, one of these two is not really necessary. So it said that if they look like this, they should be concave. And if they look like this, they should be convex. Okay, and obviously when they are equality, they should be both concave and convex. It means that they should be linear. Now, these would ensure that your your set would be convex. Okay, but a convex set might have a weird representation like this too. So obviously this is a subset of that convex set. But now for these, we have an algorithm to solve them. Okay, so and there are different algorithms to solve them. The one that we talked about was active set methods. Were active set methods. And even the active set methods, we didn't really use them for general convex programs. We only used them for something that we call quadratic programs. Okay. Now, so what were quadratic programs? Quadratic programs were the ones that not only we had this set to be convex with these characteristics, but also the objective function should be a quadratic function. So what's a quadratic function? It's ax2 plus bx plus c if it's one-dimensional. Okay, or if it's more than one dimension, it's x transpose qx plus c transpose x plus d. Or you can put a half there, or you don't put a half there. That's not really important. Let's put the half there because having the half would make taking derivatives easy. Okay. Now, a d part is not really important because the fixed part. So this is called the quadratic program. So we call this thing a quadratic program. And quadratic programs have really nice properties. If you remember, we derived that KKT conditions for the whole convex program. And there was that weird M function, M matrix happening somewhere, which we had to check at a KKT point if the M matrix is positive definite or semi-positive definite, which was a pain. The good thing about quadratic program is that that condition is automatically satisfied. You even don't need to worry about that one. So I'm not going to go over that. Just go look at your notes. This was a one-page note somewhere that said that you had to double-check that if the derivative is 0, if the Hessian is positive definite, negative definite. But the good thing about quadratic program is that even that thing is satisfied automatically. So the only thing that you need to check is the KKT conditions. Basically, in a more than one-dimensional optimization problem, you can look at the KKT condition as the equivalent of first derivative and the Hessian as the equivalent of the second derivative. So I'm just saying that don't worry even about the second derivative because it's a quadratic function. The second derivative criteria is for you, it's automatically satisfied. Everything is nice. So you only have to check the first derivative. Wherever the first derivative is equal to 0, you're fine. That's it. Now, the active set method was doing nothing more than this. It was going over your feasible set, looking at different points, and checking if they are a KKT point or not. If it found the first one, done. It said this is a local optimum. And since our program is a convex program, a local optimum is a global optimum. Nice. So we are using the fact that it's quadratic program in the sense that we wouldn't check the second derivative. We are using the fact that this is a convex program in the sense that when we find the local optimum, we just say, well, it's also the global optimum. So we are using a lot of these things. So instead of looking at these huge nonlinear stuff that we have no idea how to solve, we looked at the convex programs. Even among them, we looked at a small subset which looks like this, and even among them, we looked at the smaller subset which is only the quadratic program, and then we gave a method to solve them. So this is where the active set method kicks in. So let's see what really an active set method step is doing. The mechanics of it is not really an important thing, I would say. You know, if you have problems with the mechanics, just come to my office and we can do one step together. It's not really a big deal. Just we have to write down the equations, which is exactly the only thing. We can go over it together. But the big picture is a very important thing, to know what's really happening there. The idea is the optimal point is some point in your set, okay? And it's either, and some of the constraints are active there, and some of the constraints are not active. This sum might mean all, okay? So maybe none of them is active, maybe all of them are active. Some of them are active. So the active set method says, okay, pick some of them, make them active, look at the best among all the points that are there, look at the best one. If this best one was your optimum, you're fine. Otherwise, your optimum is not among in this set. Go look at another set. Now it just starts looking at different sets until you find the best one. So basically, let's look at it in a two-dimensional case. The two-dimensional case has a small problem, but it's not really that bad. Okay. Assume that we are solving this guy. The problem with two-dimensional case is that whenever two constraints are active, I just have 1 point. And I don't want this to happen. So I'm going to give you an intuition of what's happening. Assume we start from here. So really a starting point is not, let's even forget this. Assume that I start from here. So I start from a point inside. Which constraints are active? None. So none of them are active. So the active method would say, okay, keep all that are active, which means none. So forget all the constraints. Just look at the unconstrained problem. Now look at the derivatives. Take the derivative, set it equal to 0, find the optimal point. Okay. You do it, you find that the optimal point is, if you're lucky, you find the optimal point is here. Okay. So the active set method would tell you, okay, from here, go to here. And when you come to here, you have found the optimum. Nice. Everything happened. You found the optimizer. Good. You were lucky. Basically, the global optimum The optimum over the whole R2 was just this point. And if you constrain and put down, just throw out some points which are not optimal, you wouldn't lose anything. But this is very rare. You normally don't get this lucky. So what happens is that point falls here, outside. Okay. Now, so the first thing is that you solve the unconstrained problem. It fell here. Now you want to move this way. You want to come here. But when you want to come here, you have to check if you are violating any of your constraints or not. Then this is the step that you calculate. So up to now, you have calculated the direction that you want to go. Now you want to check how far you can go. For that one, you check your constraints. This constraint would tell you go as far as you want. I don't care. This constraint would tell you the same. This constraint would tell you the same. This one would tell you come to here, not more than here. This one would tell you not more than here, and this one would tell you not more than here. Obviously, you have to take the minimum. So from here, you come here and you hit here and stop here. This would be the first stage. Now, when you come here and stop here, now you have to check if this is an optimal point or not. Optimal point for the constraint problem, not unconstrained problem. So you check the KKT conditions. Basically, you check the gradient condition. You check the signs for the V values. You check it, you see that this is a KKT point. Now you got again lucky. If it is the KKT point, this means that this is the optimum for the constraint problem. So this is your optimizer. But you check it and you see, no, this is not a KKT point, unfortunately. And if it's not a KKT point, you have to find another direction. Okay. Now, let's see how you find the direction. You say that I'm standing on this constraint. Okay. Give me the best point on this constraint. Okay. That's that step that you solve the minimized gradient f of x, the subject to AD equals to 0. Where this AD equal to 0 came from? We know that this point was a point that satisfied this constraint, this set of constraints, meaning that AX was equal to B. Now we want to go to somewhere on this line, meaning that we want to go to x plus d, which x plus d is also on this line, meaning that ax plus d would also equal to b, meaning that ax plus ad would equal to b. But ax was equal to b, so these two cancel out. This is 0. So that's where this constraint came from. So you put this constraint there, and then you solve the problem again. Now, what would it do? It will tell you, okay, I'm really using bad colors. So I came here. Now, from here, you start searching on this constraint for the best point. It turns out that the best point on this constraint is here. Okay. On this constraint, keeping on this line, this is the best point. You come here. You haven't hit any constraint, so you got here. Now, when you get here, again, it's a new point. The first thing to do, to check if it's optimal or not. So you check the KKT conditions. It turns out that this is not optimal. But now you know something else. You know that if you want to remain on this line, this is the best you can do. But the KKT conditions are telling you this is not the best point in general. So it means don't look for the best on this line. Look for it somewhere else. Meaning, drop this constraint. This constraint shouldn't be in your optimization problem. It means that your best point is not on this line. Where are you looking at it here? In our case, since it's a two-dimensional case, dropping this one means that just solve the unconstrained problem. And since we started from here, this is not going to happen in our case. In our case, we're going to stop here, and this would be a KKT point. But assume that I started from here. Okay. So I started from here. I came here. Now it tells me drop the here. Okay. I started really bad. Let's talk about it later. It's not really important for our case. It's not really important. Okay. So assume I started from here and got here. Okay. Now, it tells me drop this, meaning that you should look for your point in the unconstrained problem. You look at your point in unconstrained problem, it tells you come here in the middle. You come here, fine. You found the optimal, you are done. So you just continue this thing. This is a two-dimensional case. Unfortunately, you cannot draw it in a good two-dimensional picture. But look at it like this. Assume this is a three-dimensional picture. Everything comes out. Okay? This is just an intersection of it. Okay, the same picture is that. Assume that I come and hit this constraint. Now I have to, now the next step would be to look at the line which is coming outside the whiteboard and find the optimum there. Okay. So what the active set method is doing, the big picture is this. It picks a point, any point, okay, and keeps the constraints which are active. For example, if we are looking in a space, three-dimensional space, and we are on a plane, it says, okay, on this plane, look for the best point. You find the best point, and then you have a test, KKT, to check if this best point is the best point for the whole problem. You check it, it's not. If the best point on this plane is not the best point for the whole problem, it means that the best point for the whole problem is not on this plane. So you leave the plane, you go somewhere else, to some other plane. You look for it for some other plane. You find it. Now, sometimes, which means normally in our case, it would end up that some constraints would be active, some constraints would not be active in the general case, in the optimum point. It means that at some constraints active in some hyperplane, on it you will find your optimal solution. But sometimes it's not the case. Like, I think it's like, no, it's not your, I'm not sure about your homework, if it's like that or not. But it's a very easy question to look at. Look at this problem. This is x, this is y. Minimize x to the power of 2 plus y to the power of 2. What's the optimum here? 0 and 0. Okay, this is clear that the optimum here is 0, 0. Okay, now assume that you are looking at this in a constraint setting, meaning that these are your constraints. Okay, and we want to solve it using active set methods, starting from this point. Okay, let's see what happens. At the first step, you check this point, KKT conditions. It's not optimal, so you have to move. Okay, this is the first step. This is not optimal, you have to move. Now, you solve your problem keeping only and only this constraint active. What would be the best point? And this constraint? Yeah, when it intersects here. This would be the best point on this constraint. And so the active set method would tell you from here, go into this direction until you hit here. And since you're not going to cut any of the constraints, you're fine. Okay? So you come here. Then you check the KKT conditions. It turns out that this is not the optimal. Sorry. You solve for D, you solve for the direction to go, and it tells you don't go anywhere. This is the best place on this line. You check the KKT conditions, they tell you this is not the optimal. Meaning what? Meaning by staying on this line, you cannot do anything. You can't do better. So you have to drop this constraint because it's not the optimal because of the KKT conditions. So you drop this constraint, now your problem becomes an unconstrained problem without anything. And we minimize this function without anything. Just take the derivative, say it's equal to 0, it will be 0, 0. So it would shoot you inside and you will end up here. So solving an active set method, you will start from here. First, you would maximize over the constraint that you are there, but then you would realize that you even didn't need to stay on this constraint. So you drop the constraint and you come here. Sometimes this is the case, but if your objective looked like this, okay, you started from here, it would, let's say, shoot you, it wants to shoot you, okay, oh, this is a good example. Now, assume that this is your so assume that this is your feasible set now, and you start from here. First, you want to optimize over this line. So you want to come here, but you're going to hit this constraint and you're going to stop here. So from here, you're going to come here. Okay. But then when you come here and you check the KKT points, you check the KKT condition, you see it's not optimal. And you check the sign for V's, it tells you that the sign for this constraint is not correct. So you drop this constraint and only look on this constraint. But when you look at this constraint, it will shoot you here. And when you get here, this will be your best point because the other one is out of it. So this is the general picture. In 2 dimensions, since it's only line, you cannot really play a lot. But you can think of it in a 3-dimensional object. Being on one plane, moving to find the best place, then you realize it's not the best one. So you leave the plane, you go somewhere else, you just look for it. This is what's going to do the active set. This is the big picture. Now, for this thing to work, we need our things to look like this, and we are not even checking the second derivative Hessian because we are looking at a what do we call it? Quadratic thing. If it's not quadratic, each of these steps, there would be a huge computation for checking the second derivative event. A KKT condition wouldn't be enough. But since we're in quadratic case, we know that the KKT conditions are enough. This is a big picture of happening in the QPs. Now, the mechanics is just what you did in the class. You know, you wrote down those things, you know, gradient condition, sine of V, these things going ahead. Questions? Have a good day.
Okay, let's